For any help regarding computer network assignment help, visit https://computernetworkassignmenthelp.com/https://computernetworkassignmenthelp.com. Email support@computernetworkassignmenthelp.com, support@computernetworkassignmenthelp.com, or call us at +1 678 648 4277. Problem 1. New operations for skip lists. This problem will demonstrate that skip lists, and some augmentations of skip lists, can answer some queries about nearby elements efficiently. In a dynamic set data structure, the query finger search x, k is given a node x in the data structure and a key k, and it must return a node y in the data structure that contains key k. You may assume that such a node y in fact appears in the data structure. The goal is for finger search to run faster when nodes x and y are nearby in the data structure. A. Write pseudocode for finger search x, k for skip lists. Assume all keys in the skip list are distinct. Assume that the given node x is in the level 0 list, and the operation should return a node y that stores k in the level 0 list. Your algorithm should run in O, LGM, steps with high probability, where m equals 1 plus rank x dot key minus rank k. Here, rank k refers to the rank index of a key k in the sorted order of the dynamic set when the procedure is invoked. High probability here is with respect to m. More precisely, for any positive integer alpha, your algorithm should run in O, LGM, time with probability at least 1 minus m1 alpha. The constant implicit in this O may depend on alpha. Analyze your algorithm carefully. In writing your code, you may assume that the implementation of skip lists stores both a minus infinity at the front of each level as well as a plus infinity as the last element on each level. ComputerNetworkAssignmentHelp.com. Solution: for each node x, we use fields key x, the key stored in node x level x, the level of the linked list containing x next x, the next element in the list containing x previous x, the previous element in the list containing x up x, the element in the level x, plus one list containing key x down x, the element in the level x, minus one list containing key x. The procedure call is finger search x, k, where x is a level 0 node in the skip list and k equals key x is a key that we assume appears in the skip list. The procedure returns a level 0 node y such that k equals key y. We present code for the case where k key x, the case where k key x is symmetric. The algorithm proceeds in two phases. In the first phase, we ascend levels as quickly as possible and move to the right, going as far as possible while maintaining the invariant key next z less than or equal to k. ComputerNetworkAssignmentHelp.com. Finger search x, k. 1z equals x2 do forever, 3 if up, z equals nil and key next, up a z less than or equal to k 4z equals up, z, 5 else if key next a z less than or equal to k 6z equals next a z, 7 else break. In the second phase, we move to the right as quickly as possible and descend until we reach the level 0 node containing key k. This maintains the invariant key z less than or equal to k. 1 do forever, 2 if key next a z less than or equal to k 3z equals next a z, for else if level z equals 0 5z equals down z, 6 else return z. To see why this takes time O, LGM, with high probability, we first prove a high probability bound on the highest level reached during the finger search. Lemma 1 let beta be any positive integer. With probability at least 1 minus m1 beta, the highest level reached by finger search is at most beta plus 1 LGM. Proof: the only keys that appear at nodes that the search visits are in the range from key x to k inclusive. There are m keys in this range. ComputerNetworkAssignmentHelp.com. For any C, the probability that any particular key in this range appears at a node in 1 list at level C LGM is at most 2 C LGM equals MC. Therefore, by a union bound, the probability that any of these M keys appears at a level C LGM is at most MC less than or equal to MC1 minus 1. Taking C equals beta plus 1 gives the result. Now fix C equals beta plus 1. To analyze the time for finger search, x, k, we use the following lemma, from lecture, and from problem set 4. Lemma 2. Let beta be any positive integer. With probability at least 1 minus m1 beta, the number of coin tosses required to obtain C LGM heads is O, LGM. The constant in the O depends on cand. Now consider the behavior of the algorithm. During the first phase of execution, identify heads with moving up a level and tails with moving to the right. During the second phase, identify heads with moving down a level and tails with moving to the right. The lemma implies that, with probability at least 1 minus m1 beta, both of the following happen. 1. The first CLGM levels of the upward part of the search, or the entire upward part of the search if it finishes within CLGM levels, take time O, LGM. The behavior is like the reverse of a skip list search operation conducted from right to left, truncated to consider only the bottom CLGM levels. 2. The final CLGM levels of the downward part of the search take time O, LGM. The behavior is like the last steps of an ordinary skip list search operation. Computer Network Assignment Help.com. To complete the proof that the algorithm takes time O, LGM, with high probability, fix beta equals alpha plus 1. A union bound tells us that, with probability at least 1 minus m2 beta, both of the following hold. The number of levels visited by the search is at most CLGM, and the bottom CLGM levels of the search complete within time O, LGM. In other words, with probability at least 1 minus m2 beta, the entire search completes within time O, LGM. Since 211 m beta less than or equal to m alpha, this implies that with probability at least 1 minus m alpha, the search completes within time O, LGM. Another query on a dynamic set is rank search, x, are given a node x in the data structure and positive integer r, return a node y in the data structure that contains the key whose rank is rank x plus r. You may assume that such a node appears in the data structure. Rank search can be implemented efficiently in skip lists, but this requires augmenting the nodes of the skip list with new information. B. Define a way of augmenting skip lists that will support efficient rank search, and show that your augmentation does not increase the usual high probability order of magnitude time bounds for the search, insert, and delete operations. Computer Network Assignment Help.com. Solution: this addition does not affect the search operation. For insert k, while finding the right location for k in the level 0 list, we add 1 to the count of every node from which we move down. When we insert the new key in a node x in the level 0 list, we set count x equals 1. Then, when we insert key k in a node y in a higher level list, we compute count y by adding the counts for all nodes in the next lower level list that contain keys in the range k, key, next, y. We also reduce count previous y by the new value of count y. The additional cost for insert is O, LGN, with high probability with respect to n, as we can see by another application of lemma. For delete k, for each node y that gets removed, at any level, we increase count previous y by count y minus 1. This addition does not affect the search operation. For insert k, while finding the right location for k in the level 0 list, we add 1 to the count of every node from which we move down. When we insert the new key in a node x in the level 0 list, we set count x equals 1. Then, when we insert key k in a node y in a higher level list, we compute count y by adding the counts for all nodes